Hi everyone. So today we're going to have a very interesting topic about the usage of Scala in the hardware design ecosystem. Indeed, there is a library called a Chisel, which is used to design chips in Scala. And today my guest is Jack Koenig, who is a staff software engineer at SiFive and also one of the maintainers of Chisel. So please welcome Jack. Thank you, Jack, for joining. I'm very happy to have you here.
Thanks so much. I really appreciate being invited on the podcast.
So I wanted to start with something simple. So can you a bit talk about Chisel? So what is it and what can we use it for?
Yeah, of course. So I have given many talks about Chisel, and you can find them on YouTube for anyone who's interested. But typically when I present about Chisel, I'm talking to a hardware audience. And the background that I assume is very different than what I typically, than what I'm expecting most listeners of your podcast to have. So this is going to be a little bit of a long answer, but I will hopefully explain enough that people at least have some idea of what Chisel is. So put simply, Chisel is a hardware generation language, and it's essentially a library or framework. What's the difference? I don't know, but it's a library in Scala where you have access to hardware primitives, and then you write a Scala program using these hardware primitives. Mm-hmm. During the execution of that program, so not compilation, but the execution of the program, Chisel will create a hardware graph that implements the design that you described. Now, what does any of that really mean? So what is a hardware generation language? Well, hardware generation language is a term that we made up, the Chisel developers, before I was involved, but we made up to distinguish it from more traditional hardware description languages. Now, some people listening may have heard of Verilog or VHDL, but if you haven't, don't worry. I will talk through all of this. So to define this, I have to talk about what is hardware description. So simply put, hardware description is just a programming language for describing circuits. Mm-hmm. Now that's a very broad term, right? That could include things like analog, right? So, hopefully most people are familiar with analog versus digital, but just in case, analog is, think waves, right? Think like sound waves or radio waves, right? Think a guitar amp or a 5G modem or 5G antenna, I should say, in your cell phone. And if you think about it, what you do with these waves, right? These waves, you're encoding information. And mm-hmm. the way you typically do that is based on the amplitude or the frequency of the wave. And you may have heard terms AM and FM. AM is amplitude modulation, FM is frequency modulation. You can encode information. And the thing about analog is that any given point you sample the wave, and any given point can have many values, right? You may have a wave and say its value is anywhere from 0 to 123. And that's great for encoding information, but the problem with it is that it's really susceptible to noise, right? That's mm-hmm. why, with an older AM radio, which is more analog than FM, which is a bit more somewhere between analog and digital, with an AM radio, if you stick it next to something that interferes with it, I don't know if microwaves interfere with AM radios, they might, but you can have noise that interferes with the signal, right? Digital, instead, at any given point, it's 0 or 1. And mm-hmm. These two more extreme ends make it much easier to describe information without noise and without loss. And that's really important. So I'm making this distinction because while analog is incredibly important, Chisel has nothing to do with it. And the vast majority of hardware design, when people say that, they're implying digital design. Not always, but almost always people mean digital design. And then one additional thing I want to add on top of that is what's called synchronous digital design. So you've certainly heard the term gigahertz, right? You think about a processor speed in gigahertz. And what a gigahertz is
it's a clock, right?
It's clock, right? Synchronous means you have a clock. Mm-hmm. And 1 gigahertz is 1 billion steps of this clock per 1 billion cycles of this clock per second. And this is really important because you don't need a clock to design hardware, and most analog circuits don't have a clock. You don't have a clock in an amp, but it makes the design much, much simpler. It's a really important abstraction. I don't really have a great analogy for it, but it's almost like functions, It's like if you didn't have a clock, hardware design is just so much harder to do that you can't design complex circuits. So basically everything I'm going to talk about from now on assumes you have a clock, because it's just such a key abstraction that you kind of need it. Okay, so now we were talking about synchronous digital designs. And I'm going to define one more thing before I lose everyone. And that is, there's one other abstraction that's pretty critical in hardware design and critical to Chisel, which is called RTL, which is register transfer level. This is, again, such a common abstraction that, when you have, say, Scala code, the generic term people use to refer to it is usually code. They'll say, you have some code. Well, RTL is so ubiquitous that when you have Verilog code or Chisel, people will often just refer to it as RTL. Even though Verilog doesn't have to be RTL, Verilog has multiple design paradigms in it. People just call it RTL because this is by far the most common. And what RTL is...
What does RTL stands for? What is it?
It's register transfer level.
Okay, yeah.
So, and what that means is it's kind of referring to the primitives that you're using. So the primitives in register transfer level are, first and foremost, registers. What is a register? This may, for those of you who've taken compilers, this will sound similar to the ISA, the instruction set architecture defined registers that your code compiles to. It's not the same as those, although the name is similar for a reason. A register is it's a bit of logic that can retain a value over a clock cycle. We call it state. It's how when you go from one cycle to the next, how do we keep track of information? You can keep some,
yeah.
Exactly. Because the other primitives, it is sort of like a variable. And variables map to registers when you compile normal code. It is like a variable, but there are other primitives. There are two other main primitives to talk about. One, which is the simplest of all, is just a wire. That's an electrical wire that carries a value, 0 or 1. And that does not retain the value, so it must be driven by a register. And then we have logic. And logic is what you're probably thinking of, AND gates, OR gates, NOT gates. Right? And so register transfer level is you have registers, you have wires and logic, and then you have registers. And that's the primitives of almost all digital design today.
I see.
So basically, an HDL like Verilog or VHDL gives you those primitives, and then you can write code to describe your hardware. Chisel provides the same primitives, except embedded in Scala, such that you write a Scala program to describe your hardware.
Got it.
And that's what Chisel is.
So when you write your code in Chisel, you say it's once you run it, it's going to produce something. So it's not a compilation. And what is essentially the result of the execution? What is the end result?
That's a great question. So putting it simply, we generate Verilog. So Verilog is by far the industry standard hardware description language. VHDL is popular too, and it's honestly probably a better language than Verilog, but Verilog is more common and better supported by tooling. So we generate Verilog. Now that's only part of the story. We actually have a compiler underneath Chisel. So what Chisel actually emits is our own intermediate representation that we call Fertile. And hopefully most people listening are familiar with intermediate formats. You have Scala 3 has Tasty. Almost everyone's probably heard of LLVM, which is built around LLVM IR. And we have our own IR. Now, our compiler is actually implemented. The compiler that implements Fertile and compiles Fertile down to Verilog is implemented. It's called Circuit. It's a really cool project for people who are listening to this and are interested in hardware. Chisel's one piece of it, but Circuit is another great place. It's Circuit, CIRCT. And Circuit is a great place where there's kind of a wider community where it doesn't only support Chisel, it supports other things. But Fertile which supports Chisel, is an important piece of it. So Circuit is part of LLVM. It uses MLIR, which is multi-level intermediate representation, which you can kind of think about. LLVM is an IR for like C, C++, and it's also used by Rust and Swift, but they also have stuff on top of it. MLIR is taking LLVM and generalizing it for making compilers. So it's not so much about a specific IR, but it's how do you describe IRs and compile them. And so Circuit is implemented with MLIR. As much as I love Scala and the original Fertile compiler was written in Scala, and maybe the Scala developers will disagree with me a bit, but compilers is an area where more direct control over your memory kind of matters. I think the memory use was cut cut to a third or a quarter when we migrated to this compiler. So anyway, what Chisel really emits is Fertile, and then we compile Fertile down to Verilog. But the relationship between Fertile and Chisel is very close.
Okay.
If that makes sense.
So to understand the full pipeline, so you write your code in Chisel, which is Scala. It goes to Fertile, then Verilog.
Mm-hmm.
Then
that's right.
What is after Verilog? Like, let's say if I eventually want to get, so what is the end result essentially?
Yeah. What do you do with hardware?
Yeah.
So that's a fantastic question. And of course you can write Verilog manually. What do you do with Verilog? So the primary focus of hardware design is making chips of digital design. And so there are tools that are there is an open source community, and it keeps growing, and it's, actually usable these days, which is amazing because, when I started 10 years ago, the open source for this tooling I'm going to talk about basically didn't exist. But the thing that you have underneath Verilog, well, there's two directions. One is simulation, and you spend a lot of time running simulations. And then the other direction is synthesis. And synthesis is sort of like a compiler. It's very analogous to compiling your normal programming language to assembly. We synthesize from the input language, Verilog, to what's called a netlist. And a netlist is just a lower representation of those registers and the logic gates. So for example, in Verilog, you can write A plus B. Well, there's no hardware for plus. There is combinations of ands and or gates that can implement it. And just to, make it very interesting, there's a lot of different ways to implement it. So one thing that's just so important in hardware, and it's hard to describe this to software people. Like, I know in software performance matters, kind of, except when it doesn't. But in hardware, everything is about timing. Everything is about, it's really hard to make a chip run at 3 or 4 gigahertz. You only have something like 15 to 20 levels of logic. So there's only a very small amount of work that you can actually do per clock cycle. You cannot do a full addition of 64-bit numbers in one clock cycle in modern processes. So there's a lot of work, or you can, but you'll be throwing a ton of hardware at it. So it's constantly trade-offs between how much hardware am I going to use? Like, how much area does the logic take on my, it's physical. These are physical chips, right? So how much area is this going to take versus how much power is it going to use? And running faster uses more power. So it's one of the biggest things in hardware is trying to find a way to make something not need to run fast, because then you can tweak the type of transistors you use to use less power. And that's like really powerful. It's a really important technique.
Yeah, I understand. And also, I guess you need like the size of your chip, like, because it needs to fit on a phone or like on different like devices. You can't have
Yeah, so maybe I'll talk a bit more about, okay, so you got your synthesized netlist, but that's just a database, basically. What do you do with that?
Okay.
Once you've run synthesis, it's not physically placed yet. It's just, it has been transformed from the higher level format to a lower level format, sort of like I said, sort of like assembly, but you now may want to, you now actually have to make it fit in the physical world. And so then the next step is called place and route. And this is when you take all the logic and registers that you need and you place them physically, and then you connect them with wires. And this is all of these, by the way, all these algorithms are like NP hard or just NP. So they're all like, basically there's a lot of heuristics and non-determinism here in what result you get. But fortunately tools do this. It used to be back in like the 70s and 80s, people would draw, on a piece of paper. And so the term we use for taking a design and pushing it all the way to a database that you can send to what we call fabs, like a fabrication plant to build it. We call that taping out, because traditionally your design was like on paper and you like would draw it. So anyway, when you want to make a chip, you get it down, you have synthesized it to logic, you have taken that logic, you have physically placed it in a space, and then you send that design to a fabrication, to a fab. Now, there are a handful of fabs. There aren't very many. Intel famously has its own fabs, but most companies are fabless. You may have heard the term fabless semiconductor company, like Qualcomm, for example. And what they do is they send their design to the two main, there's three main companies that you can buy fabbing from. Intel's trying to become one, but the main ones are TSMC. It's by far the biggest, Taiwan Semiconductor Manufacturing Corporation. There's Samsung in Korea, and there's Global Foundries. But only Samsung and TSMC are doing the highest performance stuff these days. But the area matters so much because the things that are fabbed are called wafers. So they're, I don't know, yay big. And each, in order to, in the modern technologies, in order to, let me think about how to describe this. So the way wafers are created is it's like optics and chemical engineering and all kinds of things that go into it. Because what they basically do is they have this like silicon substrate. And then with lasers, they etch things into it, and then they grow crystals, and then they etch it off, and then they wash it, and they do all this stuff. And in order to do this, you have to create these masks. Masks are like pieces of metal that are used to, say, like guide the lasers, and potentially used in the chemical washing and stuff like that. So
it's like a mold, but like a mold in foundry, but for like very low. I mean, at a tiny level, right?
It's like a really high tech mold. For really tiny things, because a chip that's like yay big may have 1 billion transistors, or more these days. So, but the problem is that this is really expensive. So creating a mask set for modern technologies, like in the sub 5 nanometer technology, we're talking millions of dollars. I don't know the exact numbers, and if I knew, I couldn't say, but it's like $10-20 million, something like that. So what that means is the area you use is extremely expensive, because then of course you have to manufacture each wafer, and each wafer still costs tens of thousands of dollars. Even you paid the upfront cost to get the mask made, but you still have to fabricate each wafer. And so the area you use is directly related to the cost of the chip. And if the bigger your chip is, the fewer chips you can fit, and the higher per unit cost. And of course, people are used to paying pennies for chips, right? I think that the most expensive chips out there in their per unit costs are probably, I don't know this for sure, but it's probably like Apple SoCs in your cell phone. And I don't know what those aren't sold, so you can't really put a value on them. But I think people typically say that the per unit cost of those is tens of dollars to $100.
Yeah.
And that's like really high. Most things are pennies.
But I guess it's because it's mass produced that they make money.
The cost only goes down that far because they're making, tens of millions of these. If you wanted to make 10, well, good luck. Now, all that sounds very depressing if you're interested in hardware design, but the good news is that this isn't the only way to do it. So you can use older technologies, and it's much, much, much cheaper. There's this, what is it called? I will find the link and send it to you. There's this kind of like open chip group that will that you can buy space on their for, and it's more like tens to hundreds of dollars to use a really old technology, and you can get a chip made, and it's super cool. It's like, this is amazing. This has only existed for a few years now. It's incredible that you can, as just a hobbyist, get a chip made. And then the way that most hobbyists, most hardware hobbyists, what they do is there are these things called FPGAs.
Yeah.
That's a term that many people have heard. What is it? It stands for Field Programmable Gate Array, and you can kind of think about it as like a reprogrammable logic substrate. So I said that we have registers and we have logic. Well, FPGAs have registers and logic that you can reprogram the connections between them.
It's like a programmable hardware, right?
It is exactly that. And, they don't perform nearly as fast as silicon as a real chip, but it's maybe 10x slower than
it's not that bad.
An actual chip, which is not that bad considering software is often, if a simulation is 1,000 to 10,000 times slower. Yeah. So, and so FPGAs they're used heavily in my industry for modeling. We use them to run faster simulations of the design we're trying to build, but they're also used as a product in themselves. So FPGAs are commonly used in, I think medical devices use them a lot. Because if you need something that runs faster than it would on a CPU, but you don't want to spend tens of millions of dollars, FPGAs are this nice in between.
So it's a good compromise, right?
Right. And you can reprogram it. So the problem with the chip is you can't patch it. If it's broken, it's broken. An FPGA, you can just reprogram it.
It was going to say that if you discover a bug or some kind of security issue, you can't fix a chip. Once it's printed, it's printed, right?
Right. That is true. There is a thing in chips called chicken bits, and they're called chicken bits because you're too chicken to commit to your feature. So it is possible to disable features that you've added a chicken bit for, but you have to build the hardware to do that.
So it's like a feature flag, but for hardware.
Exactly. Yeah. Yes, I know that I'm not super familiar with a lot of more advanced software things, but I know that it's getting common that you have feature flags, right? You send out a new version of your thing with it disabled, and then you can just enable it, and then you can disable it if it doesn't work, right? But you have to write logic to do that, right? That doesn't come for free. So, if you're disabling a feature in hardware, you literally now have extra logic that will prevent it from operating if that bit is set.
And it takes space, I guess, because the things that you disable is not useless, and
it's still there.
It's still there.
Yeah. It still costs money because it took area, but it may just not be operating. And this has happened many times. I mean, I think there was a famous issue with transactional memory in some older Intel chips, and they just had to disable it. But that was several years ago now.
Cool. Interesting. Yeah, so it's impressive, because I really know nothing about hardware, but I didn't know there were so many steps, so many, the pipeline was so long between essentially the chip and the language you write originally. Mm-hmm. So does it mean that in your industry, or maybe in your job, so you write Chisel code, this is eventually compiled to, you say, eventually Verilog, but is it then manually updated, or someone is going to tweak it, or is it every other step is kind of automatic in this pipeline?
Yeah, that's a great question. So I will say it's semi-automatic. So there are tools that do this, synthesis and place and route you use tools to do them. But as I mentioned, because the algorithms are so complicated, you can't just take a blob of Verilog, throw it at it and say, give me a great chip. And that doesn't work. So there's a lot of manual work that goes into first partitioning the design into smaller pieces, but that you need to do intelligently. It's I know that this part of the logic is going to live near together, and this part will be over here. There's no reason that I have to do these together and cause the algorithm to struggle. I can just split it at those 2 points, physically design them separately, and then connect them at the end. So there's a lot of work that goes into that. There's things called floor plans. So
this is more to guide the optimizer to do it as you want. It's like a hint, mm-hmm. right?
Yeah. Imagine if in software, you had to, and you do this sort of, right? You do this with functions, but imagine if you had to somehow take certain these 8 lines of code and be okay, these have to be compiled completely separately from all of this, and the language won't do that for you, which means you have to pull it out of your file, and it's sort of if you want to split code out into a library, you have to pull it out and make it a library. Well, we have to do that all over the place. You can't just expect the tool to handle a large design. You have to split it up manually, and it's pretty painful. And provide a lot of tips. And also the types of tips that you need to the guidance you need to give is it's a very skilled profession. So the people who do this, it is a very specific skill set of knowing how to get the tool to do what you want. Now this is partially probably because the hardware world is so proprietary. So there's only 2 or 3 vendors that you can buy these tools from. And so there's not a lot of motivation for them to make it super easy to use. And of course, there's a community of people who are skilled at using them. The open source community will hopefully help with that. The idea, one of the great things about open source is that by having an open source implementation, it can put pressure on the proprietary implementations to get better.
Yeah,
in the open source world, people can accept a 10% worse performance for 100 times easier to use. So yeah, that competition for open source and just the general increased availability, I think, will help with all of this, but it's still extremely difficult to actually get a chip made. FPGAs are a lot better. It's funny because if you go try one out, you will think the tools are really hard to use compared to what you're used to, but they're 10 times easier to use than if you're trying to build an actual chip.
Yeah, I can imagine. So do you think it would be possible to make a small demo just to visualize a bit, how Chisel look like, and maybe have a look maybe at Verilog, the output of the code, just to see the difference?
Yeah, of course. And I can also use this as like a little getting started pitch. So let me share my screen. So I have here just, you can see my VS Code. Great.
Yeah, I can see
This is just a normal VS Code window, and which VS Code has a browser, and I can go to the Chisel website, which is chisellang.org, based on the scalalang.org. And so if you click our Getting Started button, it will take you to installation. And of course, I will say that this tends to be geared more towards hardware people. So hopefully anyone in the Scala community listening to this podcast will already have Scala CLI installed, but it's very easy to do if you haven't. And then we have created a Scala CLI Getting Started example that is pretty easy to use. And then, this button's in the way. Okay, I need to open the terminal here, and I can run that curl script, or that curl, run the curl program to download the file, and then I can open it here in VS Code. And so this is a single file example of how to use Chisel that you can download the latest version from our website. I mentioned earlier that Chisel is a library. Chisel is actually a library and a compiler plugin. The main thing the compiler plugin does is allows us to track the names of values to the emitted Verilog, because it's really important that the Verilog somewhat reflects the
so you can debug like this variable in Verilog, it looks at this variable in my Chisel code.
Yeah. And so, you can just run this with Scala CLI, which I'm doing here at the bottom in the terminal. And this by default just prints it to standard out. And you can see the printed Verilog. Now I'm going to tweak this to...
Can you make your ID slightly bigger, the font slightly bigger, if you don't mind? Yeah.
Is that better? One more?
It's better, yeah.
I can do one more.
Cool.
So
nice.
You can see this. This is not very... I don't know why this is the example we have, because this is like a meaningless circuit. But it emits Verilog, and I'm going to change it to emit a file, because then I can open it in VS Code, and that will have syntax highlighting, which I think is nice. So it emits, you'll notice it's called foo.sv, which is the same name as the class here.
Yeah, okay.
And here we have the Verilog. And this is a very simple example, and you'll find that this Verilog looks maybe side by side. You will see that this Verilog looks almost identical to the Chisel, which does not illustrate why Chisel is useful, but it does illustrate that kind of like how... Well, yes, and kind of like how you can write Scala, that's Java++. You can write Chisel, that's Verilog++. Like this is basically a one-to-one comparison. One other thing I want to note that's really important in Chisel, and this will come up later, is, so I'm currently stripping debug info, but I'm going to stop doing that because one of the things that we spend a lot of time and effort on is source locators. So it doesn't show up very well, but you can see here that every line that you use to generate your Verilog can be tracked back to the Scala. Let me make this a little bigger. So yeah, that's a very basic introduction. Now, if you want, we can design a more interesting circuit and walk through that process. But
if you don't mind, because I have no idea, what kind of circuit, I don't know if it's realistic or not, but maybe let's say, I don't know, is it possible to do something like, let's say if you want to have a light that is flashing, I don't know, or I don't know,
that would be a much better demo. If I had an FPGA with me, or a way to simulate a light flashing, I would. But instead, what I think I'll do is we use greatest common divisor as sort of like so GCD is sort of like the hello world of hardware design.
Yeah.
And so, in software, I could write that as, GCD. It takes two arguments, returns a result. And then we can use the simple iterative subtraction implementation. So, if A equals B, you just return A. Else, if A is greater than B, you recurse and you subtract B from A. And if otherwise, if A is not greater than B, then that means they're equal to each other, or
lower,
or B is greater than A, and then you can just do the opposite. You subtract A from B.
Yeah, maybe else if.
Yep. And then just simply like 36 and 24 say, is 12 is the GCD, right? So this is very easy and simple to write in software. It's a little bit more annoying to write in hardware, but we can still do it. So let me comment this out for a moment. And we can create a module. So basically modules are, they're kind of the unit of reuse in Verilog. And so we also use them in Chisel. And as a class, you can have inputs. So I can have input A. We'll just give it a width. We can have input B.
So these are represent like the input of your circuits, like
Yeah, these are just wires.
Yeah,
and
exactly.
Fundamentally, at some point, if you're building a chip, then eventually at the very top, they will correspond to pins on the chip, like actual physical pins. But if we're just thinking about a block, this is a block that has wires. And wires don't actually have direction. Like electrical things don't really, there's nothing stopping you. We're not putting, not fuses. Anyway, we're not putting things that actually force the circuit to go one way, the electricity to flow one direction. It's just that for our own human sake, we have to assign direction to things and how we use it, which makes design much simpler. Now, this is a similar interface to what you have in software, but this is not enough, because a thing to remember about hardware is it is physical things on a circuit that are always functioning. You don't call hardware. Hardware is just always there. So kind of there's an implicit input in software that you don't think about, which is the invocation of the function is an operation that you're doing. And the returning is an operation, right? These are all things happening with the call stack, but you don't see it in the software you write, but it's actually part of the implementation. In hardware, we have to represent this with more ports. So I have a Boolean input to say I'm starting, like let's load some values. And I have to have a result to say when an output to say when the value's done. Otherwise, you don't know when it's finished operating, because it can take multiple clock cycles.
Okay, yeah, because the operation takes some time to calculate, right?
It'll take multiple clock cycles to calculate. Now, that's not always true. You could create a combinational version of GCD, probably, but the problem is that then it really depends on how big your inputs are and how big the circuit is. If you do it using multiple clock cycles and having state, then you can implement something that's more similar to this and how a human thinks about it, but it takes multiple cycles to execute. So,
okay, got it.
Sort of like the state when you're doing this recursive GCD is on the stack via your arguments. We have to have state. So we have registers.
And here, typically, who is going to set up the start? So because let's say you feed the input, the A and B, and do you expect, I don't know, someone, when he wants to invoke or use this function, is going to also set up this Boolean flag as well? Or
That's right.
Okay.
So yeah, exactly. You will, whatever is using this GCD, let's say for some reason you had a GCD accelerator in your CPU, right? You've got your adder, you've got your subtractor, your multiplier, you have your GCDer for some reason. Then when your CPU decides it's running the GCD function, it will drive the start up. And then when the result is done, it will do something with the output. That's called valid. That's valid based design. You have a valid bit associated with your payload. One step further than that I'm not going to get into here is called decoupled design or ready valid design, where you have ready going one direction. You have valid and your data going one way. You have ready going the other way, because for example, the GCD may not be ready yet, right? It might be busy. It might be computing a value. So that, adds more complexity that I'm not going to show here just because it would take more time. But typically you end up the way you create things to where, because if you don't have ready here, then that means manually in your design, you have to worry about making sure you don't ask the GCD to start the next one before it's done with the previous one.
Yeah.
Yeah.
I think the thing with software is that, you don't need to think about is someone else calling my function, because, you can call it as many times as you want, as long as you have memory. But I guess with hardware, as you said, if something is used, you
had to statically create it.
Yeah, it's
so
interesting.
One thing that's interesting, this will be interesting to Scala people, is, we're not using if else here. We're using Chisel constructs called when and otherwise. And this dot otherwise looks funny, but the way it works is when is, it's a function that returns a value that you can call otherwise on. Is how that's implemented. And so when I start the GCD, I have to load my state. And then otherwise, if we're not starting, then that means we are doing the processing. And so I can do this logic here, right? I can say when x is greater than y, then x will get x minus y. Otherwise, y will get y minus x. Mm-hmm. And so this is essentially the equivalent of this.
Got it. Yeah.
And then, of course, we need to return a value. How do we know when we're done? We are done when x equals y. And then an interesting thing in hardware is the result value is just always connected to x. An important thing in hardware is that very often your output is always it's always being driven by some register, but the value won't be interesting until the associated valid bit is set.
Got it.
And then it's interesting. And that's when it's actually done. So this is a direct implementation of this circuit. And we can take a look at the Verilog.
Okay. So here, essentially, you're saying that, the output of your program is always the value of the register. So you kind of like put a wire between the resistor and the output. Mm-hmm. And so essentially it's just your Boolean variable that determine if it's worth to look up the result or not.
That's right. You could look at it earlier, but it won't be meaningful. It'll be garbage.
Makes sense.
It's sort of like reading uninitialized memory. You can sort of think about hardware design as lousy with uninitialized values, and you have to be really careful. And here's the generated circuit. Maybe I'll get rid of the source. Well, they're at least a different color. But and again, this looks extremely similar to the Chisel that we wrote.
Thanks for the demo, Jack. That was great. Now, I wanted to ask you quite a different questions about the background of Chisel. So could you tell me why the original developers chose to use Scala for it?
And this is kind of a fun one because, the people who were originally creating it was just before my time. They didn't know Scala. This is like 2009 or something. But they were at Berkeley on the 5th floor of Soda Hall, which is the CS building. And on the 4th, and they were in this lab called the Par Lab, and they wanted to make chips. But the people on the 4th floor were these folks who were really interested in this new thing called big data. And that was called the AMP Lab. And a project came out of there that you might have heard of called Spark. And, by sheer proximity and friendship, the people who created Spark were the people who told the chip designers, hey, you should try out Scala. It's cool.
I see.
And I think that's kind of a fun... because you would not think that Chisel has anything to do with Spark, and it doesn't technically. But, the people who created Spark were the people who introduced Scala to the folks who made Chisel.
Okay, cool. So if there was no Spark, they would probably know Chisel wouldn't exist, or it wouldn't be in Scala.
It probably wouldn't be in Scala. The original version of Chisel was in Ruby and was really bad, apparently. I don't know. I never saw it. And then the second version was in Chisel. It was in Scala. I don't know what else they would have picked at the time, though. I mean, probably, I don't know, because they wanted to switch from Ruby because it was too slow. Like interpreted languages were too slow. So they wouldn't have picked Python. And I would say today there are some nice languages to choose. I don't know what I would have picked in 2009.
Yeah, so you don't know what was the reason why they chose Scala at the time? What was the driving factor? So you said like mostly the speed and...
Well, and, it's great for embedded languages. Like, there are things that some languages are really opinionated on. Like this is not really a thing much anymore, but like there are some languages where you can't overload symbols, right? You can't like define the plus operator. And that's just like, come on, like you're out if you can't do that. But Scala is just good for embedded languages, and it has pithy syntax. Like it's very concise, and it's very fast for what we need it to be.
Nice. And so generally, is Chisel used mostly like in the academia, or is it something more in the industry, or is it both? Like who are the main users of Chisel?
Yeah, so that's a great question. So Chisel was originally created at Berkeley by academics who wanted to create chips. And when you only have a small number of people, you want to be more productive. So it was created by people who want to be more productive. Now, the software industry is sometimes pretty conservative. It's really hard at a company to introduce a new programming language. And some of that's because of hiring, but sometimes it's people are worried about performance. They're worried that the abstraction overhead of Scala may be too much compared to the Java they were writing. And there's extremely analogous concerns from industry with Chisel, which is if I write Chisel, I'm gonna have less control over the Verilog, because if it's Verilog, I can just modify it. Well, with Chisel generating it, what if I can't tweak something I want to tweak?
Yeah.
And the concerns are around what we call QOR, which is quality of result. And that's just a term we use to refer to the power use of the design, the performance of the design, and the area it uses, also called PPA. Now, those concerns I understand. And of course, when you use the analogy of Scala versus Java, yes, of course, you can write Scala in a particular way that's more similar to Java. But canonical Scala is slower than canonical Java because there's a bit more abstraction overhead with immutable data structures. Even if it's usually worth it, there is some overhead. Such overhead is not acceptable in hardware. So in hardware, there has to be no abstraction overhead. So it's important to remember that Chisel we are not converting Scala to Verilog. We are letting you write a program to describe the hardware you want. So there's actually no abstraction overhead in the Verilog you get. Now, people are skeptical of that claim in the industry, but for example, at my employer, SiFive, where we use Chisel extensively, we have to compete on the performance, power, and area of our designs. And we've had 400 design wins and over 2 billion chips shipped, which is sort of my existence proof that you can build high performance real designs with Chisel. And fortunately, because of our success in doing so, the skepticism from industry has dropped a lot. There's a lot more people using it. I would not say it's, Chisel is less popular in the hardware world than Scala is in the software world, but there are often pockets at different large companies using it. And so, who's using it? It's really both. It's both industry and academia. And, one other thing I wanted to mention is, as a library maintainer, it's really hard to know who's using your thing, your code. Sometimes they comment, if you break something, you'll hear. Yeah. It's always really nice when you accidentally broke something because that's what gets people active. But I liked in your podcast episode with Li Haoyi, you asked him about his libraries and Scala CLI, which I thought was funny because I use his libraries with Scala CLI all the time. I use it to replace anything I would have done in Python. I now do that way in Scala CLI, even at work. But he said no one talks to him about his libraries, and sometimes I feel the same way.
Yeah,
so
I think
it's hard to know.
It's a tragedy. No one talks when they're happy about something. We take it as, we like it, we take it for granted, yep. But we only talk about something when it doesn't work. So yeah, you're right. It's difficult. And so, but so go ahead, Jack.
Well, I was just going to say, we don't really have great metrics, but if you look at GitHub stars, Chisel is kind of close to. Chisel has 3.9 thousand. Cats is at 5.2. Yes. So we're kind of in the ballpark, a bit less, of course, but kind of in the ballpark of some of the more popular-ish Scala libraries. Now, of course, Spark has 39,000, so that's a different planet. But,
but also the usage is more niche. I think there is probably more people who work in data science than there are people who work in your area, like in design of hardware. So,
of course.
I
I think more people use cats relatively to the number of stars than people who use Chisel, but it's a metric that we have.
Yeah, sure. And so what is the selling point of Chisel comparing to other things? So how do you compare? What are the other alternatives? So you can write Verilog directly. This is an option. Mm-hmm. What are the other options you can do? And how does it compare to those?
Yeah, that's a great question. So I do want to there are two other hardware generation languages or hardware description languages embedded in Scala that are, anyone interested should also look at. There's Defiant HDL, which is primarily by Oren Port. I think he's on the Scala SIP committee, and he's a fantastic, kind of collaborator. At least, we don't work on the same project, but we work in the same area. So he does a great job of relaying, hardware concerns to, the Scala developers. And then there's another similar. So he's focusing on different types of abstraction. So I talked about abstraction overhead. Chisel is focused on none. He's looking at alternative ways of describing hardware that there may be some overhead. There might be, there might not be, but it might be easier to write complex circuits, which can be an advantage. And I think that's really cool. And he's done some really cool things in Scala 3. There's another one called Spinal HDL by Charles Papon, which is more similar to Chisel. The main difference between Chisel and Spinal is that the developers of Chisel were focused on building ASICs. So we focused really hard on that. Charles is more in the hobbyist community where they tend to use more FPGAs. And so he's done a lot of stuff to make it easier to use with FPGAs, which is great. I wish Chisel had more of that. But My focus, my employer's focus is on building chips, so that's our focus. So I'm not really going to compare much to them because to some extent it's almost like flavor and a little bit of what your focus is on. But compared to something like Verilog, it really is. It's hard to explain concisely how much more powerful Chisel is than Verilog. It's sort of like if someone asks you the same question, what's hard to do in Java that's easy to do in Scala. And of course, a functional programming enthusiast will start talking about effect systems. And as soon as they said that, they've lost 99% of Java programmers, and they didn't even get to name drop Chisel, right? Whereas you can alternatively go talk about syntax, and you can say Scala is more concise syntax, it has better type inference, it has functions as values. But those things are just simple enough that for someone who hasn't really used it, they can just be like, that's just syntax, or I don't mind the extra typing. I think it makes the code more clear. Now, I think most people listening to your podcast are probably, pretty interested in Scala, invested in Scala. And so they understand why these things are useful, but it's really hard to explain it.
Yeah, it's difficult to sell.
I can give one example that I think is a good one. So I'll give a simple example and then a more complicated one. So the simple example is in Chisel, it's really easy to define, user-defined types. We call them bundles, but they're basically structs. And they can even be bidirectional. So I talked about how on a decoupled interface, a ready valid interface, you have your data, your payload, and your valid going one way, and your ready going the other way. That's back pressure. So Verilog has structs, but they can't be bidirectional. And it's also kind of hard to type parameterize things. You can, but most of the time in Verilog, you just deal with essentially, we call them uints, which is essentially just a vector, like a bit vector, just a bunch of bits. Whereas as humans, we want richer types. We want to think about our data with a name, right? And with separate fields. So in Chisel, it's much easier to define user-defined types. And this is going to sound very simple, but it's amazing how much of an impact this has. It's really easy in Chisel. It's one line to take my complicated data type and connect it to my complicated data type. But in Verilog, usually your data is not organized in that way. And so you end up with one line per field. And then if you want to move something around, you copy paste the 20 lines of connection that you had and have to update it.
Yeah.
And it's truly mind-boggling how much time people spend just moving wires around. And whereas
it's also error-prone, I guess.
Yeah, and it's error-prone. Now, Verilog is not a safe language at all now, just like in C++. Now the compilers have linters that are pretty good. So there's decent static analysis, but it took years to get that static analysis to the state it's in today. And it's because the language doesn't enforce anything.
Yeah, I understand. So yeah, I guess it's the thing with all higher order language, it's easier to write stuff. So you make less mistakes and you're maybe more productive as well. Yeah. Also.
And it's easier to reuse what you've already written, and it's easier to refactor. And that's hard to explain. It's something that you kind of have to experience. Let me give one more example, though, because this one doesn't have quite the same analogies in software, but to hardware people, I hope some hardware people listen to this podcast episode, and I think this one will resonate, which is, a microprocessor, a CPU. What it basically does, it takes instructions, and it executes them, right? So an instruction might be add this register to this register and put it in this register. If you've ever looked at the output of your compiled code from C, that's what it is basically. So an important step in CPUs is called decoding, where you take that instruction and you decode it into the control signals that will control the rest of your logic to implement the instruction. You don't want to have specialized hardware for every single instruction. That would be incredibly expensive. So for example, your ALU, your arithmetic logic unit, will have a multiplier and an adder. So depending on which instruction you're using, it will tell certain control bits which logic you're using, what to activate, basically. So the way you implement a decoder, in basically every single company you can think of that designs CPUs, they have an Excel spreadsheet. They put every single instruction, and there are hundreds of instructions, but if you actually look at them, you will subdivide them further for various reasons. So you will have hundreds to thousands of lines in this spreadsheet. And then you will have the signals you want to map to, the decoded signals you want to map to corresponding. And then it will be someone's job to take this spreadsheet. They will, convert it to another format, turn it into a table, and feed it to this program called Espresso. Espresso is like the best logic minimizer. It's so good that it's basically unchanged since like 1992. That code is so old, it's not even written in C89, and it will not compile out of the box with modern C compilers. You actually have to edit the code a bit to compile it with a modern C compiler. But it's so good that, I'm not kidding, everyone is using it. And so you take that table, you send it to this logic minimizer, and it spits out a minimized table, a somewhat smaller table than you put in. And then what people do is they write a Perl or Python script. And yes, I said Perl. Perl is still incredibly popular in the hardware industry. And they will print Verilog to implement that table. And that's how you build a decoder.
Wow.
Okay, that sounds insane because it kind of is. In Chisel, you can write arbitrary Scala. So you can write Scala that you can write your table in Chisel. You can invoke the process of espresso in Chisel. You can ingest the output and turn it into Chisel. And that takes like 200-ish lines of Scala, and it's in our standard library.
So you said like you write Chisel, you put it on, and it generates new Chisel at the end. So it's like optimized Chisel, or
so we're not generating Chisel. That's a great question. I should clarify. It's the way this works in the Chisel standard library. We're not generating Chisel. What happens is you've taken that table, you've invoked a process to call espresso, you've brought the result back in. Then you can sort of think about it as like, it's almost like interpreting the result. You can write a Chisel generator. Like Chisel is highly parameterized. You can parameterize it with whatever you want. You can read a JSON and do arbitrary things. So you read that table of essentially it's a mapping of like 0101000 to 0000101.
Mm-hmm.
And you can write Chisel that can ingest that format and generate logic to implement it.
Okay.
And so, but this only takes, this entire thing is like less than 200 lines of Scala code. And I'm not kidding when I say everybody does this with an Excel spreadsheet and custom scripts. In fact,
it's automatic.
So ubiquitous. We did this in undergrad. We wrote our own version of this. Everyone does it. And it's like, why? Why is this not a library that you can just use? Well, in Chisel it is.
Got it. Yeah, it sounds very painful. And I think also something like, I guess, like as a company, I guess if you if you create many chips, many of them probably have similar functions, or maybe you're writing like a new version of an existing chip. So you kind of want to take the existing one and changing slightly. And this is where I guess like the power of a higher order language that allow you to refactor and add stuff to it is good, because I guess if you want to, with Verilog, if you take just your Verilog and want to add something to it, it may not be so straightforward. Like that's my guess, but.
And that is incredibly insightful, because that is exactly like one of our competitive advantages. And we're not secret about it. This is what we do. We write, when we design a processor, it's parameterized. And so we will have different product lines with different numbers, but it comes from the same generator. The same program will generate both. And it allows us to be a lot more productive, because if you fix a bug in one, you fix it in all. And when you're writing, in out of order processors, there's all kinds of knobs. If you go and, rest in peace to AnonTech, because that was one of the best websites for people interested in hardware, because anytime a new chip would come out from Intel, Apple, Qualcomm, they would like really dig into it and tell you, the reorder buffer, which is an important structure in out of order processors, it has 108 entries, for example. Mm-hmm. And how they figure that out is really neat, because of course the companies don't tell you this. There's just programs you can run and measure the performance to figure out the size of structures if you kind of know what you're looking for. But 108 is a number, but why not 116? Why not 96? Why not 156? Right? And it's really easy in Chisel to make that a parameter. And then on the lower end chip, you scale it down. On the higher end chip, you scale it up. Mm-hmm. And lower end doesn't mean, lower end may not be the way to describe it, because the smaller structures uses less power. So if you don't need the performance, right? If you're running, the processor in a cell phone versus the processor in a watch are kind of similar, but the watch needs to use a lot less power, but also you're not going to play video games on it. So it doesn't need to be as performant. So with the same generator, we can do both. And in Verilog, that's just like, you kind of can sometimes, but not really. Most of the time, if you're taking a chip that you put in a phone and then you're making a derivative product for a watch, you copy paste the Verilog and you start editing.
Yeah, and I guess also there is a thing is that I mean, of course, the chip we have on our phone or on our computer needs to be extremely efficient. But I guess like if you take the total number of chips that exist, like on, like, let's say a remote you have for your garage door or something like this, all this sort of stuff is like, doesn't require any kind of performance. So here is where it's more important to be convenient and to be able to maybe tweak it than to be able to be fast, because anyway, it's very dumb, right?
Yeah, that's right. And of course, one thing I should note as well is that the chip in your phone, the main SoC, and SoC is system on the chip, because there's a lot more on there than the application core, the main CPUs. But the main application core on your phone is very different from the chip in your remote, the CPU in your remote. And so I wouldn't say that we have one generator for both of those. Those are like different families.
Yeah, of course.
But the thing is though, that CPU in your remote is similar to, there are thousands of CPU cores in the SoC on your phone. Now there's only maybe 4 or 8 of application ones, but there's a ton of little ones doing things like power management, keeping track of your modem. And those chips, those little tiny CPU cores actually do look kind of like the one in your remote. And so by having a generator for that, we can still tweak what it can do. And there's all kinds of areas where it's not just about performance. Like one thing that's really common is like, a CPU that runs code isn't useful if it can't talk to the outside world. So one of the most important things are what we call peripheral devices. And a thing that's really, really easy for us to do, and it's kind of hard to do in Verilog, is parameterize the number of peripherals you can talk to. So if you go to like SparkFun or one of these websites where you can buy like, I cannot think of the name of them, but hobbyist chips, like a Raspberry Pi is a really high-end version of this, but there's lower end ones too. If you go buy one of these, they'll usually have like, there's some number of devices you can control. Maybe you have a USB controller, maybe you can control 8 general purpose IO pins, maybe you can control 2 PWMs, which are pulse width modulators. Those are useful for driving motors and stuff. Well, if we have a customer come to us and say, we want to control 10 PWMs, that's like really easy for us to do. Just turn the number up. For a traditional Verilog design, you're going to have to go do manual work to make it to where that thing that you're selling that only control 2, because that's all most people want, control 10.
Got it. Yeah, definitely. I mean, I can see the competitive advantages of being able to move fast and iterate. Mm-hmm. Sounds good.
And reuse. Reuse is the biggest thing. It's reuse. That's why we write libraries. That's why everything is about reuse.
And when you write your Chisel code, so first, like, what version of Scala do you support? Is it Scala 2 or Scala 3 at the moment?
Yeah. So this is a fun moment to be having this conversation, because we are currently only supporting Scala 2.13, but we are also actively upgrading to Scala 3. So it's finally, like, we've been talking about it for like 2 years, but Scala 3 is so great. There's so many things I'm so excited about. And, while you do use Chisel with other Scala libraries, it's not quite the same. Like, you're never like stuck on 2.13 because of Spark if you're writing Chisel. Yeah. Like, Chisel does not run on web servers. Chisel is more of like a thing you run. You just like, it's like a script. You like run it, get a result, done. So we have none of those issues. For us, it's more just effort. And so currently just Scala 2.13, but we are working on Scala 3, but it's a bit of a process.
And what is the biggest blocker? Is it because you use macros inside of Chisel, or what is it?
Yeah, it is exactly that. So we have found that upgrading normal code is pretty easy. Xsource 3 is great. It works really well. It's really easy. It takes 2 hours. There's a bit more details whenever we turn on Xsource 3, because we also realized there's all kinds of features or behavior of Scala 2 that we were surprised by. That, for example, if you put an access modifier on a case class constructor, it doesn't affect the companion apply or the copy method. That I had no idea. And it's like, well, no, we wanted those to be private. So we're also changing a few APIs in the process, which is breaking, but like, people aren't supposed to be using these anyway. So it's longer. It's not just turning on Xsource 3. We also have to like make release notes for the things that we're making private, whatever. But that is like, just getting it work is like an hour or 2 hours probably. But we use a lot of macros. And I do think the macro system in Scala 3 is really good. And for some kinds of macros, like type class derivation, it's actually not that really, I don't think the migration is that painful. You just have to write the code. Yeah, okay, it might take a while. It's a lot more than 2 hours, but like, I like the macro system in Scala 3. And I think, at least with the experiments I've run, that type of macro is pretty easy to do. But we do something different that's extremely painful, which is we use macros that affect our public API. And because, if you think about like type class derivation, right? The public API of type class derivation is really just basically you just have like an implicit, showable of A.
Mm-hmm.
That doesn't really touch your public API very much. You just implement a different way to materialize your showable. But our macros are the public API. The simple example of this that most people will be familiar with are type tags, right? So if you use a type tag in your public API, you now have to split your code into your shared code and then source main Scala 2 and source main Scala 3, right?
Mm-hmm.
But we take that and dial it up to 1,000,000. So we have this particular macro. It's called, so let me take a step back. In that demo, you saw source locators, right? You saw the line of Scala in your Verilog.
Yeah.
Well, the way you implement that is just with an implicit, and then the materialization of the implicit can grab the line number, the file and line number. That's great. Works wonderful. The problem is that if you are using implicits in your APIs and then you want to chain calls to apply, you can't do that by default in Scala 2. So what I mean by this is, like, imagine you had a function that takes an implicit argument that returns a list, and then you immediately want to index that list. You will get, like with just parentheses, you'll get an ambiguity error. Scala will complain and say it will say wrong type, expected source info got int.
Mm-hmm.
And for most Scala people, that's fine, because one, there aren't that many functions that take implicits, and there are even fewer of them returning types that you might want to call apply on immediately. And Scala users are pretty comfortable with that kind of error message. Unfortunately, we deemed, like, people coming from hardware were not very comfortable with that, and it was a huge blocker for people coming to Chisel. So what we did is we implemented this thing called our source info transform. And what that does is, in order to allow you to chain an apply call immediately after basically any of our public functions, we have a macro where the function you're calling, the original function you call, is called whatever. Let's say it's called head, right? So you call head, it does not take an implicit. Instead, it's implemented with a macro. That macro will rewrite head into do_head, which takes the same arguments, but then adds the implicit.
Mm-hmm.
And so what this macro does is it disambiguates, such that if you then immediately chain and apply, there's no implicit on the head function. The macro expands after the compiler has figured out that you've chained apply.
Yeah, I got it.
So in Scala 3, this is all just fixed by using, because in order to pass a given or using parameter, I don't know the right
you need to
terminology,
prepend it like with
you have to use the keyword, which is amazing because it completely solves the problem. But all of our public APIs are using this macro. So what I did just a week or two ago is I went in and I call them veneers. Is like I had to split our public APIs into source main Scala and source main Scala 2. So there's like files that are hundreds of lines long, and all they are is def head equals macro source info transform, def do head full signature equals, and then calls head impl, which is a protected method in source main Scala.
Yeah, so I guess one of the big difficulty you face is the fact that you want to maintain both Scala 2.13 and Scala 3 at the same time. Like, I guess if you were going to say, okay, I abandoned Scala 2.13 and I move to Scala 3, it may not be too difficult, but it's the fact that you need to maintain both, which makes sense,
Right. The fact is that for at least a little while, we have to cross compile.
Yeah, definitely.
And we want them to be as close as possible because we want it to be really easy for Chisel users to upgrade to Scala 3. And I think it will be. I think that like we are feeling some pain, and for users, I think Xsource 3, and then they should be good to go. Maybe change their Scala C options and their build flow, but
Makes sense. Cool. So one thing also you mentioned that I found quite interesting. So most, I guess, users of Chisel are people that come from a hardware design background, right? They're not very, let's say, like a standard backend developer that goes into hardware design. Like, is that correct?
Right. Yeah. Most people coming to Chisel come from a hardware background. Not everyone, though. And ironically, I think the people coming from software who are interested in hardware are the happiest, because they try Verilog and they're like, what is this? And then they try Chisel and they're like, okay, like this is like that's kind of okay. Yeah. But yeah, it's most people who do hardware design, or most people who write Chisel, come from a hardware design background. And so for them, we're trying to teach them software engineering because there is very little software engineering in the hardware world.
Yeah. So I was wondering, like, so how difficult it is for people who come from a hardware design background to onboard and like with Chisel and try it out, like how, because I guess it's they're probably not familiar with the JVM, they're probably not familiar with Scala or functional programming. So I understand that you try to make the syntax relatively similar to Verilog, but it's still a big jump. So what is your experience with like training people or onboarding people into Chisel?
Yeah, that's a really good question. I think that it's one of these things where like Chisel 101 is really easy. Like the basic introduction, as long as we give you something on the rails, like a reasonable tutorial, or if you're at our company, then of course we have the internal build flow. So you don't have to, like, they don't have to even know what the JVM is to use Chisel. But let's say you're running it on your own laptop, right? Then as long as we make that pretty easy, and I think Scala CLI has been the greatest thing ever for the simple introduction. But getting people to write very basic Chisel and generate Verilog, trivial. But it's the next step, what I might call Chisel 201, where it's often very hard. And not some hardware people do have some software background, right? They may just love Haskell, or they may do hobby projects in Rust. And for folks who have some experience in a more modern programming language, and even Python, if you write more modern Python and use things like MyPy, if you like think about Python that way as opposed to throwaway scripts, for most of them, it's pretty easy. But for people who are truly hardware background, like they know Verilog, they might know C, they might know Python for scripts only, you're basically teaching software engineering. And that's a difficult thing to do. A lot of people, most people are bright, most people love to learn, and they pick it up, but it does sometimes take time. So they might be productive in the small, but it does take a while sometimes to get people with no software engineering background to the level of modifying our generators, because they're complicated. They're parameterized for a reason. It's sort of like you've taken an introduction to C class and then you try and modify the Linux kernel, and you quit because Linus yelled at you because you didn't know what you were doing, right? It can be tricky.
Yeah, I guess it's always this thing with like when you have an introduction to a programming language and when you see it in an existing project with like thousands of files, and there is always a difference. Even though it is the same language, the scale of it is quite different.
Yep. And so it's very important. I think what internally we found is so important. So one thing I should know in hardware, unit testing is like barely a thing. And so part of the most important thing that we do when we teach new people is how to write unit tests, because then you can always feel productive.
I see.
Because you can always try your ideas. Like, yes, this is going into a large thing that's too complicated to unit test for whatever reason. It's bad, but in hardware, that's often the case. Maybe that's too hard to unit test, but you can take that thing you were building and test just it. You can write a function in Chisel, you can test it, and then that same thing will work when you plop it down in the big thing.
Talking about testing, so how do you test your Chisel code? So how does it even work? Like because I guess you don't test the Verilog that you generate. You want to test the function that you're producing. I mean
so we actually do test the Verilog basically.
Oh, you do test the Verilog. Okay.
In the past we had an interpreter for Chisel, or for Fertile, I should say. You can't really test Chisel directly because the execution of the program creates the artifact that you need to test. But you could test the Fertile is fairly close to Chisel. Like if you write a register in Chisel, you have a register in Fertile. It's very close. So we had an interpreter when we switched from the old Scala implementation of our compiler to the new one in MLIR. That unfortunately was one of the casualties, but there is a new interpreter for Circuit coming, so hopefully we'll have an interpreter again in the not so distant future. But setting that aside, you test the Verilog, and what that means is at a company like at our company, because we ourselves don't build chips, we sell intellectual property, we sell designs to other companies who build chips, but generally it's our customers who make the chips. So they want Verilog test benches. So we have to do some testing, unfortunately, in Verilog itself. So you write Verilog to test your Chisel. As long as you pick interfaces that are like very standardized. So in the hardware world, there are standardized buses, like a bus interface, which is what you can, it's like kind of it's a very coarse level of abstraction, but you can create your PCIe controller and that will speak AXI, which is like a standard bus interface, and then it's kind of easy, not really, but sort of easy to hook up to another AXI interface. So if you write your Verilog at that level, it's fine because that's a standard that we have to implement in Chisel anyway. So like writing Verilog against it, there's no, like the Chisel doesn't change enough for it to matter. But it's hard to unit test in Verilog. So you can write unit tests in Chisel. We have like a testing framework. You can write Scala. You can write like straight line Scala code. And then you can like drive values on the inputs and read values from the outputs and then run a simulation that way. So most testing is simulation of the Verilog.
I see. So you write the test in which language? Do you write it in Scala or do you write it in Verilog?
Both.
Both.
So for unit tests, for small things where I just want to, so in hardware, there's a whole, we don't usually use the word testing. We usually use the word verification. And it's like it's a whole discipline. And there's a lot that goes into it. There's a lot of art, randomized testing, running a lot of tests. And then there's metrics that matter to customers, which is called coverage. There's like automatic, you have this in software too. You have like line coverage, right? Well, that is taken extremely seriously in the hardware world. And there's both the automatic coverage, like line coverage, toggle coverage, which is like, did you toggle every bit? But then there's also human described coverage. Like if I have a queue, I want to check that the queue gets full, because when it's full, do things still work or do we get deadlock, right? So then humans will write their own cover points, say, I want to cover this condition.
Yeah.
And it's really important to cover all of that. So that's like large scale verification. But if you think about the goals of verification, coverage is just like a fuzzy good feeling. Like, am I done? There's also what you really care about is finding bugs, right? That's more the software mindset of testing is I want to find bugs. I want to make sure there are no bugs. So for very small unit tests, we tend to write those in Scala, and then larger scale, full suite, sign off to tell the customer we fully verified it. That's often written in System Verilog. One of the things we are working on is trying to lift more of that into Chisel, but that's a long process that we are working on.
One thing I also found interesting is that do you have the equivalent of property-based testing in Chisel? Like when you essentially, because I think it's something where, you generate random variables, you want to check general properties, like let's say your adder or whatever, if you have some like you add two things, you're sure that it's never going to be smaller than the two inputs, for example.
Yeah, so we do have that. You can use Scala test and Scala check with Chisel if you want. I think there are some aspects of that we should improve, but I'll set that aside. But you can totally do that in the normal Scala way. I will say I will actually one-up you. In hardware, we do a lot of formal verification. So in software, usually when you write properties, it's still simulation. It's randomized.
Yeah.
And you run and you simulate it to check that the properties never violated. In hardware, we do formal verification where when you have those properties, we prove it mathematically that it can't happen. Now, that's really hard to do, so you can only prove certain things, but it turns out that most of the time in processors, we said earlier you can't patch a chip, right? But you can often work around bugs in software, but the bugs that you cannot work around are, can the chip turn on, right? So what you will often find is it's really important to prove small things about the design, like prove that your reset sequence, which may take 100 cycles, can complete. And you can prove that depending on how you set it up. So yeah, we will define properties and say this can never happen. And then we will feed it to, like, have you heard of like SMT solving?
Yeah. Yeah.
So it's really common in the hardware industry to take your Verilog, send it to an SMT solver, and it will tell you if the properties you're proving are satisfiable or not. And if they are, then that means you've proven something can't happen. Now,
interesting.
That's only as good as the properties you can write. Yeah. So anyway, but yes, we do formal verification. Earlier, it was a bit easier to do that in Chisel. With an earlier version of Chisel, we had really good formal support, and you could write formal checks almost like unit tests, and it was super cool. That was another casualty of the move to the new compiler. However, very recently, similar support is showing up in Circuit, where Circuit can not only generate, Fertool is the compiler for Fertile to Verilog, but one of the related tools to it can compile your Fertile to BMC maybe. It's similar to SMT. It's a format like for formal logic, and then you can feed that to a checker. So we don't have it yet, but I'm very hopeful that will restore the ability to write formal unit tests in Chisel, which is super cool.
Yeah, definitely.
Years ago.
So what do you think are the next step in the development of Chisel? What are the things you want to change or upgrade or whatever?
Yeah, getting onto Scala 3 first and foremost. That will help with a lot of stuff. Just that stuff I was talking about with the implicits versus using. It's such a small thing, but that is like huge for us. Not to mention all the other stuff, right? Then there's two directions that also are really being looked into. We need better testing in Scala, in Chisel, I should say. We do too much of it in Verilog. We would like to do more in Scala, and there's a lot to that, a lot of pieces for that. Some of it's extensions to Chisel, some of it's just more Scala library work. The other one is the type system in Scala 3 is better, and there are some weird things. If you really look at the details of Chisel, there's some weird things about how types work where we lose Scala type safety because at the time we didn't know how to do certain things or it wasn't possible. So I think that the transparent inline macros in Scala 3 are going to give us a really powerful opportunity to give more type safety while being, so basically I created like a port, right? It was like IO of uint.
Mm-hmm.
But the type returned from that is not IO. The type is uint.
I see.
And that's kind of awkward because the objects we use to represent types are the same Scala type as the actual hardware values. And that's the reason for that is because when you have user-defined types, how can you like dot into your user-defined type if we've boxed it as a different type? Like, how do you do that? You can't do that in almost any language. Well, you can with transparent inline macros and type classes. So I think there's some really cool stuff that we can do that we're going to experiment with in Scala 3.
Nice. Okay, so essentially Scala 3 is your biggest roadblock, and then from that you can open up different stuff.
We can do this. We actually can do that in Scala 2. It just is a lot. It just doesn't work as well. Because the way the macros are, the tooling's not as good. The errors are worse. So in Scala 3, it's just a lot nicer.
And I guess also like when you know that you're going to move to Scala 3 eventually, you don't necessarily want to devote too much time into implementing it in Scala 2.
I would prefer to delete the Scala 2 code.
Yeah. That's the problem when you maintain an API is that you can't like do a big bang release. I mean, this is a problem when people actually use your code. Is that maintaining it and doing it like gradually is difficult.
Yep, users are the best and worst thing for a project.
Another thing I wanted to ask you that I forgot is you can use other libraries with Chisel, like you mentioned Scala test or Scala check, but in your typical production Chisel code that you write, do you generally use other libraries or other libraries that maybe people in the Scala community are familiar with or not?
Not that many, but it is very common for people to use JSON serialization is like super common because people will put their parameterization in a JSON file and then consume it and use that to feed their thing. So, whatever, upickle, JSON or as JSON IDER are all common choices. OSLib is common because it's the execution of your Chisel that creates the output. You kind of have to write your own main function. So people will sometimes they'll do some type of argument parsing, like, scopt. I don't actually know how people pronounce that, but scopt, scalopt, whatever. Sometimes people will use OSLib. And then probably the most interesting that I've seen is people who are doing digital signal processing, which is like when you have a 5G modem, you read in the analog values and you digitize them, but then there's a lot of, in the digital world, you can like remove noise. There's all kinds of algorithms you can apply. That's called digital signal processing. And that's very mathy. And so they use type level Spire to do some of the math. And then they can use that math to generate the hardware to implement it, which is kind of cool.
That's really cool.
Yeah. Maybe they mostly use that for testing. I can't remember if they use that for testing or if the results of calling it help them generate hardware, but they use Spire.
Are there any constraints? Like, let's say if you wanted to use another Scala library within your Chisel code, what are there any things you need to keep in mind for this or?
Not really. I mean, Chisel does have a kind of a global mutable runtime. I say global mutable, like you can't mutate it, but your Chisel function calls will. So it wouldn't work well with multi-threading at the moment. That's another thing we'd like to improve in Scala 3 is we would like to turn that, you can kind of call it like a builder context or the environment. That's kind of this like secret global thing into a given parameter. Because if you did that, then things like multi-threading would work. You could, send out stuff. So currently, the constraints would be that there is global mutation going on. So anything you can do that would make that observable would be really bad.
Yeah.
But and most of the constraints are just what you want to do, right? You don't really want to chisel web server. I mean, you could, right? If you were, there was someone I saw once made like kind of a web server where they had their Chisel generator running as a server, and then they would send requests via protobuf, and it would send back the hardware. Like, okay, I think that's a strange thing to do, but if it worked for their use case, great. And that's the cool thing about being in Scala is that's like you could just do that, right? There's nothing stopping you. It's just more, do you want to is the question. Is it useful is the question.
Yeah, no, but it's good that there is no like concrete limitation except what you mentioned. And so now let's think that, you're like a Scala developer and you want to give it a shot at Chisel. So you showed us the website, like the, startup projects. What are the best way? So this, I guess, is one way. Are there other like maybe online resources, either like maybe some kind of small project you can follow, an online course, or what? I don't know, what are the resources that people can help to get started?
By far the best resource is there's a textbook, Digital Design with Chisel, and it's free. It's online. It's open source. You can.
I'll put a link below the video.
Yes, yeah, I'll send you the link. It's called Digital Design with Chisel by Professor Martin Schoberl, and it's, like I said, it's free. You can order a print version if you want, if you prefer physical textbooks, but it's free and online. And that book is about teaching digital design. So that's great for people coming from Scala because you won't know anything about digital design. So it teaches you digital design and it teaches you Chisel. And it will go all the way through implementing a RISC-V processor at the end, which is building a processor is one of the coolest things you can do, because what happens if you build your own RISC-V processor, you can go take C code, compile it, and run it in a simulation. That is so awesome because it's like you have made something that executes code. And that textbook will walk you through all the way through building a simple processor. Now, like, I love that book. It's not as good it's great for people coming from Scala. It doesn't work as well for people coming from hardware because like they already know digital design. They're like, I don't want to learn it again. But it's fantastic for people listening to this podcast.
Awesome.
As far as courses, I wish there were more. The best courses for hardware design are usually the ones from MIT or Berkeley, which traditionally have posted all of their resources online. The course number from Berkeley is CS61C. Unfortunately, right now, the resources are not up. They are having issues with accessibility concerns, and they're working with partners to try to figure out how to make the resources accessible, and then they'll re-upload them. But even though the resources aren't as easy to find now, the lectures are still like on YouTube and on like on web archive websites. You can usually find old versions of these websites. But I think Berkeley's 61C is the best introduction. If you want to really understand hardware, if you want to spend, it is a full semester course, but if you want one thing that teaches you everything that you want to know about hardware at a pretty deep level, that's the course for it.
And do you know if there is any like kind of project? I was thinking, because I have a young child, like, maybe you want to get into programming, like, and, I think the nice thing with hardware is that you can potentially have something that you can visualize, let's say a light that is blinking or something that, do you know if there is any like resources online that can teach like, young children, like how to program these sort of things?
I don't have any offhand, unfortunately. I can try to find some to send to you to use in links, but there are like small FPGA boards that you can buy. And then those FPGA boards will have lights that you can blink, but they also will often have other peripherals. So a common tutorial that people might do is if you remember VGA, that's kind of an older video connector format. That's actually like really easy to do yourself. And so just on an FPGA, you can program the interface with VGA, and then you can like draw stuff on a monitor. Those types of things are really cool. I know they exist, but I don't have any links on.
No worries. And so did you say that Chisel, because I understand that you use Chisel mostly to build chips, but you said that it's also possible to drive like an FPGA as well, right? Oh,
right. So yes. So you can think about FPGAs sort of like alternative targets
yeah.
for implementing your hardware. So it's sort of like when you write C code, you can compile it for x86 to run on a normal Intel or AMD processor, but you can also compile it for RISC-V or ARM. And for ARM, you'll be running it on your phone, right? Or that kind of chip. So that's sort of like ASIC, which is a normal chip, or an FPGA. So yeah, you can use Chisel to program an FPGA for sure.
Awesome. Cool. Now, another thing I wanted to ask you about like the community. So let's say, I want to get into it. So you shared a couple of resources. Are there any kind of like online forums or like, chats that where, people in the Chisel community like go there to, ask questions or,
Yeah, definitely. So from our website, chiseling.org, or from our GitHub repository, github.com/chipsalliance/chisel, which I hopefully will have links below. We have links to we have a mailing list that's not as active anymore because most people now use Element, which is what used to be called Gitter. It's like a chat thing.
I knew Gitter.
We may or may not move to Discord, but regardless, if we do, the links to these are always on the website and on the GitHub repository.
Great. Cool. And in terms of funding, like, could you tell me like how is the development of Chisel funded? Is it like funded by companies, or is it mostly like people benevolent that do this on their spare time?
Yeah. So yeah, there's no direct funding. But it's mostly done, like myself and some of the other maintainers have day jobs that, I would not say I am paid to develop Chisel, but developing Chisel is part of my day job.
Okay.
Very frequently. So yeah, it's mostly like companies, I don't want to say donating time, but companies who have a vested interest in it have people who work on it.
Got it. So yeah, you can develop Chisel during your day job, and
yes,
yeah, it's part of your responsibility.
Exactly.
Cool. And so if people wants to get involved into the development of Chisel, what is the best way to do it? Like essentially, like on GitHub, is it like you have like some issues that people could tackle, or?
Yeah, we have some that are marked good first issue. Now that's something that gets stale quickly, so I'm not sure how good the current ones are, especially when you're listening to this. But I mean, the best thing to do is to pop by the Element channel and discuss. You can also always file an issue and ask. And we have a developers meeting which is also linked on the GitHub repository. It's Mondays at 9 a.m. Pacific, like California time. And it's open. There's a link. You can join, come chat. We do have several users there, and developers. And I whenever we've gotten new developers in the past, I'm always happy to spend some time chatting with them about what they want to work on and how to do it. Our developer documentation could be better, as always. But part of the move to Scala 3 is I've had to revisit a lot of our infrastructure, and so I'm planning to improve the contributing docs a bit as well.
And by the way, so I wanted to ask you, do Chisel participate to the Google Summer of Code? Because I know that some other Scala project recently, like I forgot the name, but one of my first interview was around the music in Scala. And they recently did for the Google Summer of Code. I was wondering if you have something similar.
Yeah, we have in the past a couple times. We don't usually, but that's a good reminder to me that that's maybe something we should participate in again in the future.
Okay, so potentially, if someone is interested, they could reach out, and it's potentially something you could organize.
Yeah, it's definitely possible, and then. There are other open source hardware groups who do Google Summer of Code. A really good one is FOSSI. It's the Free and Open Source Software Foundation, Free and Open Source Silicon Foundation, and the SI at the end is the atomic number or not number name of silicon. But they do Google Summer of Code, and they don't do Chisel Google Summer of Code projects specifically, but if someone trying to do an open source hardware project were interested in Chisel, they would definitely depending on what projects they have, they're generally willing to let people kind of do what they're interested in. And then, they might be the official mentor, but then I know those guys, they would get in contact with me. And
Awesome.
that's a good one to look out for is Fozzie's Google
Okay,
Summer of Go.
awesome. Same, like, if you can send me the link afterward, I'll put it below, and I think it will be helpful for people who want to get involved. Now, so another thing is that, there is the open source part and like a hobbying part, let's say, but there is also like, let's say, if you want to get a job in this area. So is your company, can you remind me, so your company is SiFive, right?
That's right. SiFive, SiFive.
And so are you guys hiring people who, require experience in Chisel or?
Yeah, so because Chisel is pretty niche, we never require it. But of course, it's nice when we do see it. We are hiring. It depends a lot on the day when you look. But SiFive.com/careers will always have the current postings. But we have offices all over the world. So, we are founded in, the San Francisco Bay Area, but we have people all across the US. We have a huge office in Taiwan. We have multiple offices in India. And then we also have offices in France and the United Kingdom. So we're all over the place. And, we have job postings at various sites all the time, kind of, sometimes a spot gets filled and then, maybe it won't be for a while. But yeah, please check that out if you're interested.
Sounds good. And could you give me an idea of the scale of the team of all, like, how many people in SiFive like use Chisel?
Yeah, that's a great question. Yeah, I'm not 100% sure what the number is, but order of a couple hundred. So we use Chisel for all of our hardware design, and so basically anyone who does design uses Chisel. Anyone who works on it or on related tools will use it somewhat, and then we use it, of course, in verification extensively. So, and design and verification are the two biggest subgroups we have in engineering. We also have like a normal software team, and it's funny because our software team is mostly for getting software to work on our designs, which tends to be lower level software. So they tend to work on things like Linux and like low level libraries. So they're mostly writing like C, C++, whereas the hardware people are writing Scala, which is a really funny inversion of what you would expect. But our software team doesn't really use Chisel, but definitely in most of engineering uses Chisel all the time.
Okay, and you say it's in the scale of 100, roughly.
Hundreds, probably.
Wow, yeah, that's impressive. Cool. Yeah, I think it's very nice. It's very nice to hear because I think from the external world, for example, I discovered Chisel only a couple of months ago, and still I work in the Scala community for a long time. So it's interesting to see it's a completely different area, something I wasn't aware at all, and I think it's extremely cool and a great idea. Yeah,
I don't remember which year it was. I want to say it was maybe 2018. Some of us went to Scale by the Bay, and one of our co-founders and our CTO, Yunsep, gave a talk, and this was the kind of talk that's fun, like in the hardware industry, is very mind-blowing, and the software people may not have seen quite how cool it was, but he gave a talk using a Google presentation and then revealed that Google presentation was running on our silicon, designed with Chisel, which is a pretty cool thing to be able to do. And so anyway, some people who are very interested in what we're doing, maybe go find his talk. It should be on YouTube, Scale by the Bay, probably 2018. But yeah,
nice.
I feel like the Scala community, many people know about us, and I feel like they see us as kind of these interesting people in the corner, and it's cool to get a bit more visibility to the wider Scala community, and so people can see kind of what we're doing.
Yeah, definitely, and I think it's good to see like one potential use case of Scala that is successful and works in the industry. That it's not like a pet project, it's not necessarily like something academic, but it's something that's used by companies, and it's a great advantages for your company to use that.
Yeah.
Awesome.
Exactly.
Right. It was amazing to talk to you, Jack. I really enjoyed to spend the time. Thank you very much for attending. Do you have anything you would like to say before we end up?
No, I think that's it. Thank you. Thank you so much for reaching out to me. It's an honor to be invited, and I'm really glad to have had this opportunity. So thank you so much.
You're welcome. Thank you, Jack. Bye.
Thanks. Bye.